Okay, we need some more help when it comes to solving a differential equation using Laplace transform. There's some more things out there that you'll run into by solving a differential equation using Laplace transform that we need to go over. And so in 7.3, we try to clarify some more terms here that we want to be able to give some light on. One is called the first translation theorem. The second would be the second translation theorem. So we're running to these two concepts. And it's going to be good that I give the test in the classroom. And when I do, I will give you this one page of the formulas. There's a lot of these translation theorems and all of, the Laplace transforms of all those various forms and the inverse transforms. I'll give that to you. I don't expect you to try to be able to pull up all this stuff from memory, being that we're somewhat rushing toward the end of the semester. And so I'll try to help you out there. These theorems will be on there as well. They're just formulas. The first translation theorem says that it's possible to evaluate the Laplace transform. Matter of fact, they'll take the first translation theorem, look at it, and then also reverse it and talk about the inverse of it as well. So I don't know if you remember, like in algebra, where you have a function and then you can shift that function over to the left, to the right, up or down. That's the same thing we're doing here. You take a Laplace transform, and it can shift as well. It can shift from the unit from s to s minus a. So if it does shift like that, you go from f of s to f of s minus a. We say that the translation is from s to s minus a. Well, here that's said to be some positive translation. So you move on the s-axis, the x-axis, if you will, over here a units to the right. If it's s plus a, then you move to the left a units as well. So what we're going to do is take the Laplace transform of f of s, take the Laplace transform of f of s, and when you do that, we're going to evaluate it as s goes from its position to s minus a. So I think that's a really cool way to do it. Now, what are they saying? That translation is when you have the Laplace transform of e to the some at times some function here, f of t. And so it's said here to now take that Laplace transform, they're going to shift it a units. Now, how does that look? Well, it looks like this. Anytime I have a Laplace transform and I have e to the at times some function, I make use of the first translation theorem. Let me show you the problem. Look at these problems here. See that e to the 10t? Then that's the translation. Here's what it says. It's very easy. It's the Laplace transform of t, but here s is shifting. You know this Laplace transform of e to the 10t is 1 over s minus 10, right? So this is basically s going from s to s minus 10. Right? So now I just evaluate the Laplace transform of t with this new position for s. Well, the Laplace transform of t is 1 over s squared. But s is going from s to s minus 10. So you just write that as 1 over s minus 10, all to be squared. Look at the next problem. See the parallel? Here I take the Laplace transform of that t to the third. Here with the translation as s goes from s to s plus 2. Well, the Laplace transform of t to the third is going to be 3 factorial, that's 6, all over s to the fourth, but s goes from s to s plus 2. So this answer is 6 all over, in parentheses, s plus 2 raised to the fourth power. Is that okay? It doesn't matter how complicated they make the problem look, you just break it down. So here what we're going to do for this problem, we're just going to expand all that out. This is t times parentheses. This is e to the t plus e to the 2t all to be squared. So this is e to the 2t using the FOIL plus 2 times e to the 3t plus e to the 4t. So I look at these transforms individually. This is the Laplace transform of t times e to the 2t plus 2 times the Laplace transform of t times e to the 3t plus the Laplace transform of t times e to the 4t. So that since they all have a t, we know that that's going to be 1 over s squared. But here for the first one, s goes from s to s minus 2. So this is 1 over s minus 2 to be squared plus 2 over here, this is s minus 3 to be squared plus 1 over s minus 4 to be squared. Is that okay? Well, if it doesn't matter about the, if it's a sign there, as long as I remember that the Laplace transform of sine kt, remember that guy is the k over, right? So it's going to be the 3 over here, s squared plus 9, but the s is shifting from s to here, s minus 1, because of here, this is e to the at, a is 1, s minus 1. So we write this as 3 all over s minus 1 to be squared plus 9. Let me jump to the inverse, and then I'll be done for today. So the same way how in 7.1 they introduced the Laplace transform, 7.2 they introduced the inverse transform. Here we'll do the inverse of that first translation theorem. Now that one's pretty cool. So basically, you have the inverse transform, but then notice that when you look at this, like this term here, oh, I can't see it now. When you look at that, it's going to be 2 functions in one. You want to be able to identify those 2 functions. And when you do that, you're going to write it as such. So the solution would be some function e to the at times that original function f of t. Now let's look at this guy and see if we can see what's happening. What I see here is, I see the Laplace transform of t squared, which is 2 all over s to the 3rd. Now there's no 2 up there, so we have to write this as 1/2 times the Laplace transform of t squared. So that's 1 over s to the 3rd. Now I also see this s plus 2, or 1 over s plus 2. So I know the Laplace transform of e to the negative 2t, I know that gives me 1 over s plus 2. Well, you put them both together, and what we have here is this e to the negative 2t times 1/2 times t squared. That becomes our answer. I got the 1/2 here times the t squared, then times this e to the negative 2t. I'd better leave you with this one. Let me work this out. I think this is the one. No, this is even better. Let me do 15 and then I'll be done. Okay? I can't leave you comfortless, because this guy, this will trip you up. Okay. So what I'm going to do here is, if I could factor that denominator, I would use partial fractions. but I can't factor it like that. So I must complete the square. So I complete the square, so this is the inverse transform. You have S. This is over S squared plus 4S. I take half of 4, I get 2. I square that 2, I get 4. So I'm going to add 4 and subtract 4 right downstairs, then plus that 5. So this is the inverse transform of that S over. Now the first 3 terms I can factor. I get S plus 2 to be squared, then plus 1. There's an S in there, can you tell? Now, here's the trick with this guy, and that's what I want to show you now so you can take the weekend to ponder over it. At S plus 2 there, I have an S up top, so I'm thinking that this somewhat resembles a cosine t, because that's equal to S all over S squared plus 1. But here, if it's cosine, whatever this term S is here, it has to be the same thing there. But this is S plus 2. I don't have an S plus 2 up top. So I have to put it in there and take it out at the same time. Right? It's like a karate strike where you strike and it's, you come back real quick. They don't see it, right? Hopefully they don't. But I'm too slow. So you saw it, right? Yes, sir. Yes. I'm doing cosine of 1 times t. Well, here my k is 1. I'm just matching up to this problem right here because I got this 1 squared right there. So my k is 1. Yes, sir. All right. So here's what I have to do for this guy. Just because with cosine, whatever that S term in the numerator, it has to be that same term downstairs. Well, I don't have S plus 2 up top. So I'm going to write this as S plus 2 minus 2, which is fine. That's still equal to S. So I didn't harm anything. So I come down here. This is the inverse transform of S plus 2 over S plus 2 to be squared plus 1. And then this is minus the inverse transform of 2 over S plus 2 to be squared plus 1. Yeah, my stomach too. Sorry about that. All right, so now this is the cosine, but also since I have this S plus 2 downstairs, this becomes e to the negative 2t times cosine of t. This is minus that 2 right here, minus 2 times e to the negative 2t, because I have a S plus 2 downstairs, times the sine of t. Here k is equal to 1, and that's the answer. Okay. I'm going to stop right there. Thank you all for staying over 5 minutes.